Good morning, everyone. Welcome to our second press conference today, and we'll focus on the polar regions. The title is Polar Regions, Arctic Sea Ice Future, Antarctic Ice Shelf Stability, and Glacial Landforms. Taking part in this press conference, we have Julian Strove, who is a senior research scientist at the University of Colorado National Snow and Ice Data Center in the US. Following her talk, we'll have James Screen, who is a senior lecturer at the Department of Mathematics at the University of Exeter in the UK. And they will focus on the Arctic. And then we'll have two speakers from the British Antarctic Survey, Jenny Turton, who is a PhD student at BAS and also at the University of Leeds in the UK, and Kelly Hogan, who is a marine geophysicist at BAS in the UK. And I'll hand over to our speakers, and at the end, we'll open the floor for questions. Thank you.
Okay, great, thanks. I should probably first mention that I'm also at University College London now, so I sort of had a joint affiliation between both institutes. So I just want to make that clear. So I'm going to talk about the shrinking sea ice, which I know everybody is probably well aware of this topic. But just to set the stage, we're just showing the time series from the satellite data record, which shows the September sea ice extent from 1979 to 2016. And the one thing I think that's interesting about what's going on in the Arctic right now is, I mean, there's a lot of year-to-year variability, but certainly we have this long-term trend, which is about 14% per decade right now in regards to the summer sea ice extent. But there is a lot of year-to-year variability, but the last 10 years have all seen the 10 lowest sea ice extents on record. And 2016 didn't set a new record low, but what I'm going to talk about in a moment is just how anomalous 2016 was in many other ways besides setting a new record low. And in wintertime, so we usually focus on the summertime because that's when the changes are most dramatic right now in the Arctic, but the winter is starting to respond as well. If you look at the time series of just the winter sea ice extent, you can see that the trends are about half of what we see for the Arctic, about 43,000 square kilometers per year versus 87,000 square kilometers per year for September. But what's interesting is the last 3 winters have had the lowest record maximum. And I don't think we've really seen that before, where we have 3 consecutive winters in a row with record low sea ice conditions in the wintertime in the Arctic. And the region that's really driving this is the Barents Sea ice. So in the Barents Sea, we seem to have persistently low sea ice cover that keeps continuing several winters in a row. And that's really what drives our winter sea ice variability. So whatever happens in the Barents Sea basically sets the stage for the Arctic as a whole during wintertime. Now, 2016 was quite unusual in many ways. And in one way, I mean, every month of the year in 2016 saw a sea ice extent that was at least 2 standard deviations below the long-term mean. And some months, May and June and October and November, were more than 3 standard deviations below the long-term mean. And that's something we hadn't seen before. I mean, we had several consecutive months with record low sea ice conditions. And of course, because of that, we had the lowest annual extent that we've recorded yet in the Arctic in 2016. And if we just look at where we are today, when we add on the last 3 months in January, February, March, again, we're tracking at the lowest levels that we've seen. So we're looking at, almost 7 consecutive months now where we've had record low sea ice conditions. And this isn't something that we've seen before, definitely in the satellite data record. And it's a little bit cautious when we think about this because just because we have these record low winter ice conditions, that doesn't necessarily mean we're going to have a record low summer sea ice extent. There really is little correlation between what happens in winter in terms of the extent and what's going to happen in summer. So there's a bit of a danger there in trying to extrapolate too far in the future. But what does matter is how thin or thick that ice is. And I actually just came back from the Arctic on Friday. I was up there for 3 weeks out in the Lincoln Sea, and we were making snow depths and sea ice thickness measurements. And we found that in general, the first-year ice was a bit thinner than usual, and it's not surprising because we had a very warm winter in the Arctic, so that would have impacted somewhat on the thermodynamic ice growth. We did find the multi-year ice was about 2.5 meters thick, so again, a bit thinner than we may expect. So that's something I think to look at more is how thick the ice is going to be as we come into the melt season. And excuse me, just to talk about kind of where we are today, I mean, we're still tracking at record low levels so far. This was just from a couple days ago, but currently sea ice extent again is still tracking at record low levels. And so it's going to be really interesting to see how this continues. In the summer, we did see, right when I was leaving the Arctic, some strong winds were starting to generate open water areas. So things are starting to break up now in the Arctic. So I think it's going to be an exciting summer. One of the things that I will be talking about in my talk later today, though, is that, and this is something that makes, I think, forecasting sea ice conditions so much more challenging, is that we see this drastic increase in sea ice variability happening. So the gray line is just showing the total sea ice extent anomaly for all months over the data record. And you can see as you get to about 2007, you're starting to see these large swings in the sea ice extent. And the 10-year moving mean variance, which is shown in red, shows you that increase in variance. And I think this is really challenging because now the Arctic is starting to respond. It's showing a lot more variability from year to year, which makes it very hard for us to predict, for example, how much ice will be left over in September, which is something that a lot of stakeholders are very interested in. Because as the ice cover thins, it's just that much more vulnerable to atmospheric circulation patterns that would favor ice melt, for example. But it's also interesting, and something I'll talk about this afternoon, is that sort of these sort of features where we see this kind of increase in variability is something we also see in climate models as you start to transition towards an ice-free Arctic state. So this might be the sign that we're starting to go towards that transition period. And finally, I thought it's always useful, I think, for us to put our changes into a longer-term context. NSIDC recently released, in the last couple of years now, an updated data set that goes back to 1850. And so it's just assimilating more data from ships and whaling log reports, other observations, and trying to reconstruct what the sea ice was in the Arctic back to about 1850. And so if I just look at the anomalies in the sea ice extent, and this is now as a function of year on the x-axis and month on the y-axis, and these are anomalies, you can see that, generally what's happening today, especially, in the last 3 decades, is quite unusual, even in that longer-term data record. There may have been periods where you had reduced sea ice cover, for example, in the 1940s, that was prominent in summer and maybe some other months, but we've never seen a time where we're seeing such low ice conditions that are year-round. It's not just in September, it's happening in all calendar months now. And then finally, I know James is going to talk more about future projections. So in November, Dirk Knotts and I published a story in Science where we were looking at the links between Arctic sea ice loss and cumulative CO2 emissions in the atmosphere. And so we find that there's a very strong linear relationship in the data with relationships to increases in CO2 in the atmosphere with a trend of about 3 square meters per metric ton of increase in CO2. And this trend is actually steeper than what a lot of our climate models are showing. And so the sensitivity seems to be larger in the real world at the moment than what the models are showing. But one of the nice things about this way of representing it is it really sort of shows, how much extra CO2 can we really put in the atmosphere before we're going to lose the Arctic sea ice. And basically, with another 1,000 gigatons of carbon, the sea ice will disappear in the summertime. So this sets sort of a limit that maybe countries can think about in terms of how much extra CO2 we can put in the atmosphere. And our current emission rates are about 35 to 40 gigatons of carbon per year. So this would mean basically the ice would be gone in the next 25 years or so. If we keep adding more CO2 in the atmosphere. And I think that'll be a nice segue for you, James.
And it's nice that our numbers agree as well.
Yeah.
There we are. Yeah, so hello everyone, good morning. I'm James Screen from the University of Exeter, and I want to pick up where Julian left off and talk a bit about the future of the Arctic sea ice. And I'm sure many of you are aware of the UN temperature goals and the temperature targets, but just to refresh memory there, we had the Paris Agreement last year, which has now come into force and has been ratified by hundreds of nation states. And in that, they talked about having a temperature target of limiting global warming to below 2 degrees C, and that's been around for quite some time now, this 2 degrees C target. But a new addition in the Paris Agreement was also to add that we should be pushing towards trying to limit global warming to 1.5 degrees, so a lower target. Now currently we're running at about 0.9 to 1 degrees global warming, so that means that we've got maybe another half a degree to go for this ambitious UN target, or about a degree for the original UN targets. Another thing to point out is that everyone that's signed up to the Paris Agreement made pledges, all the nations made pledges about what activities they would take to reduce their emissions. And people have kind of added all those things up and come to the conclusion that if we did currently what we say we're going to do, we'd end up with warming nearer to 3 degrees. So we already need to ramp up our efforts to get to 2 degrees and even more so to get to 1.5 degrees. So I'm interested in the Arctic and the sea ice. So I wanted to know really whether these temperature targets make any difference in terms of the likelihood of seeing a summers without ice. And this is something that's captivated, I think, the public imagination and scientists' interests alike. The other thing to say is if we just do nothing and we carry on business as usual, we end up with scenarios of 3 to 4 degrees. But hopefully we're not going to go down that path. So we went, basically, let's start off with a headline message. We crunched the numbers, and these are the probabilities we came up. So we're looking at the likelihood of seeing a summer without ice in the Arctic. And you can use the model projections, and we had to do some clever things to adjust for biases in the models because you can't take them just at face value. But having done that, we arrive at these numbers. And so if we were successful at limiting global warming to 1.5 degrees C, it seems that the probability of witnessing an ice-free Arctic is very low. At 2 degrees C, the probability starts to increase. So you get to a situation where limiting to 2 degrees may be sufficient, it may be not. In IPCC terms, that probability would be classed as about as likely as not. So toss a coin. And as you ramp up, obviously, towards like 3 degrees C, you start to see much greater likelihood of ice-free Arctic, getting to the point where 73% of the IPCC would call that likely. So we can essentially say from this that 1.5 degrees would be sufficient to prevent an ice-free Arctic. 2 degrees maybe, but it's not certain to be sufficient. And 3 degrees C is likely insufficient to prevent ice-free summers. So I guess I should just say a little bit more about what we actually mean by an ice-free Arctic, because I'm talking specifically here about the summer and actually September. So as Julian pointed out, September is the month of the low, in the annual cycle, it's the month with the lowest sea ice. It's also the month where we're seeing the largest trend. And scientists have kind of gravitated towards defining an ice-free Arctic as when the average cover in September falls below 1 million square kilometres. And I think some people find that slightly strange because they think, well, surely ice-free is 0, not 1 million. But the rationale for that, and if you see the map here, is that by the time you get to 1 million square kilometres, the sea ice is really tightly constrained to a small region, like there's thick ice up against the northern parts of Ellesmere Island in Greenland. But for all intensive purposes, the most of the Arctic is open water when you reach this threshold. So if you're a shipping company or something, then your Arctic sea routes, certainly on the eastern side, are open. There may be some residual ice in the Northwest Passage, but generally, that's a kind of representative pattern of what 1 million square kilometres looks like. And so it is effectively ice-free, but it's not totally ice-free. And yeah, I'm only talking about September. So the timing for ice-free conditions in other months would, of course, be later. And it's going to take a heck of a lot of warming to lose the ice in winter. I don't think any of the scenarios, even of warming of up to 4 degrees, you lose your ice completely in winter. So we're talking about summer here. And so the idea was to couch this in terms of the global warming targets of the IPCC, but people often say, well, what does that mean in terms of a year? When do you think, what year will it likely see an ice-free Arctic? The issue with that is that whereas the sensitivity to the temperature rise is largely independent of the scenario, so what pathway you take to get to 1.5 or 2 degrees, of course, the actual timing in terms of year does depend on what emissions we put into the atmosphere between now and then. But we can look at some of the scenarios that are out there in the IPCC report, and we can say that actually, so our best estimate of the first ice-free summer is around 2046. So pretty similar to what Julian was saying. And there's some like a little bit earlier than that if we have high emissions, so maybe 2040, and a bit later than that if we have lower emissions, say 2050. And there's always some uncertainty around this number. We can only really expect to predict it within about 20 years because of natural variability in the climate system. And because of that natural variability, so that was to say a best estimate, but because of natural variability, it could happen sooner than that. So I guess we tried to think, well, what's the earliest point we could feasibly see an ice-free summer? And that equates to something like 1.7 degrees of global warming, or around about like mid-2020s, 2030 kind of time frame. Again, depending on exactly what emissions pathway we take. So I think that's all my slides. But yeah, so it's nice to just reiterate here that, so this was an analysis based on climate model output, but where we adjusted for the known biases in the climate models. But it's reassuring that we arrive at pretty much the same answer relative to the 1.5 degree target, and in terms of a year, as Julienne's work, where she actually used the observed relationship between CO2 concentrations and sea ice. So we've got two different ways of coming to effectively the same answer. So if we want to save the Arctic sea ice, we really need to push for 1.5 degrees. 2 degrees may not be enough.
Hi everyone, thanks very much for joining us. I'm now going to take you from the Northern Hemisphere to the Southern Hemisphere. So I'll try and clarify a few things where springs and summers are the opposite way around. But I'm a PhD student at the British Antarctic Survey and also the University of Leeds. And I'm going to talk to you today about firn winds and how they are influencing the surface melt of an ice shelf in the Antarctic. So the Antarctic is the map in the bottom corner there. I'm sure you all have seen a map of the Antarctic before. The main flow around the Antarctic is westerly. So it kind of circles around it. It's called the circumpolar westerlies. And the figure above that is the Antarctic Peninsula. Now, this is a mountain range that's roughly the length of the UK. And the majority of it is around twice the height of Ben Nevis, around 2,000 metres. So the light grey areas on that figure are the mountains. And in the bigger figure, that's Larsen Sea ice shelf. So all of the dark grey areas are ice shelves. And these are floating extensions of ice. So they're not land ice, they kind of float on the ice. But they often act as a plug to the land ice to sort of stop it retreating straight into the ocean. And Larsen Sea ice shelf is the area that I'm working on. Now, you might have heard of the Larsen ice shelf group previously, because in 1995 and 2002, we had some catastrophic collapses of the ice. So firstly, in 1995, we lost an area that's around 1.5 times the size of Greater London. And this was the most northern ice shelf on the peninsula. And then we moved down to Larsen B, which was just above Larsen C. And that was a really big collapse. We lost 5 times the size of Greater London in just a small number of months. So if we look at the figure here, this is a satellite image. So this is in January. And you can see the darker patches are the ocean. And you can see the water that is actually on the ice shelves and sort of lines of it. And as we go through the months, we see the ice shelf completely collapse. It starts to sort of carve off in the big tabular icebergs, and then we get almost complete loss of the ice shelf. There's only 10% of this ice shelf left now. And we're starting to see some of these signs on Larsen C. So this here is a satellite image of Larsen C ice shelf, and the figure highlighted in the red is where we can see these melt pools, so these ponding of water on the ice shelf. And they've kind of got the similar pattern to what we saw over Larsen B, sort of lines of this dark water on top. And this is a figure taken just a couple of months ago from one of my colleagues at Bass, and the light pools there are these surface water. So the ice shelf is the white ice, and then the light blue is the water that's sitting on the ice. And this is a natural process in summer. You know, it does reach above freezing naturally. But we think that there are mechanisms that are enhancing the amount of melt, and one of these is firn. And the water that's created on the surface, or ponds on the surface, kind of drips down or leaks into these crevasses or cracks on the ice shelf that are naturally occurring. And the water prevents them from sort of sealing, or can make them propagate all the way down to the base of the ice shelf. And that's what we think is a major precursor for the collapse of the ice shelves that we saw over Larsen A and Larsen B. And the way we link this into firn winds is that firn winds are very hot and dry downslope winds, and they occur naturally, but they may potentially be increasing in frequency. We're trying to find that out. And they are enhancing the amount of melt on the ice shelf. So I'm going to get a little bit more technical here, but there are 2 mechanisms on the way that this air warms. So either thermodynamic, so sort of just the descent of the air down the side of the mountain means that the air parcel warms, or the potentially warmer air is brought down from above. And so that means you can have like a different airflow at the base of the mountain. And so this interaction between the airflow and the mountain is what generates these firn winds. And my work has been looking into where and when they occur. And so we found that they're actually a lot more frequent than we first thought. So this barcode here, every stripe is a firn wind for at least 6 hours. And so I looked from 2009 to 2012, and we found that there's over 200 of these episodes a year over the majority of the ice shelf. So I looked at 6 different areas, and even over 100 kilometres from the mountain where they are generated, we're still seeing the effects of these warm, dry winds. And also further south than we thought they had occurred. We'd never recorded them before as far as AWS 6 here on this figure, which is around 68 degrees south. So they're a lot more spatially extensive than we first thought they were, but they're also more frequent. And to put it into context, the Larsen Sea ice shelf is the size of Wales. So it's imagining that this firn wind happens maybe on Snowdonia, and you can still feel the impacts reaching the English border. But why should we care about that? Well, the firn winds are not only sort of observed or felt over 100 kilometres away, they're also causing melt on the ice shelf that far away. So if you look at the figure here, especially with spring, we can see that during firn winds, which are the red bar, we have significantly more surface melting with days when these firn winds occur than during normal processes. So in summer, we expect some melt, around 2 millimetres a day. But during spring, we're having an equal amount of melt as we are in summer during the firn winds. And that's significant because it's making the melt onset earlier. We're kind of expecting melt December, January, February time, but we're actually seeing it sometimes September, October in particularly frequent firn condition years. So this leads to around 40 millimetres of additional melt every year and around 8 days more of melting a year. And so this is just the figure that we've got from 100 kilometres away. It'd be really nice if we had these observations really close to the mountains where we're seeing these melt pools. But you can imagine if we're seeing them that far away, where the winds are slightly cooler, you can kind of imagine how strong they are right by the mountains, where we are seeing these melt pools in the satellite images. And so that's what I've really focused on, looking at where and when these firn winds are happening. And hopefully now we can see if we can maybe find a way of looking at how frequent they were in the past and into the future to see if their frequency is changing and what implications this will have for the Larsen Sea ice shelf. Thank you.
Thank you. Hi everyone, my name is Kelly Hogan. I'm also from the British Antarctic Survey, and I'm going to take you on more of a global tour than either of our 3 previous speakers, because I'm going to be talking to you about a new volume, a new atlas of submarine glacial landforms, and this is really, a huge piece of work that's taken a long time to put together, but what it is a collection of the highest resolution seafloor imagery that we have from both polar regions today, all in one place, going from the Arctic to the Antarctic. And what the images are showing is the fingerprint, or the way that ice interacts with and shapes the seafloor at these high latitudes. And it's taken more than 250 scientists, marine geologists, glaciologists from 75 institutions from 20 countries across the globe, about 4 years to put this all together. So this is really the first time that this kind of data set, or these data sets, have been put into one place, and we can really look at one compared to the other, but just by turning the pages. If we put together all of the seafloor coverage from each paper, and there's about 180 papers in the atlas, if we added up how much coverage of the seafloor that we've got in the atlas, it covers an area about the size of Great Britain. So we're talking thousands of square kilometres of high-resolution imagery showing how ice has affected and interacted with the seafloor. So, that's great, and this imagery is stunning and beautiful, and I can't wait to show you some of the images themselves, but, how do we get this data? So what we do is we take ships out across the up to high latitudes, and we are using acoustic methods, echo sounding methods, to ping down a sound pulse to the seafloor, record the response back up at the ship, and then we use that in a variety of ways. what I'm showing you here in the main image, if you look, that is something called multi-beam bathymetry. That's a fan of sound that's passed down to the seafloor and then comes back up to the ship. And what you end up generating, or being able to generate, is the water depth at each one of those sound pings or sound pulses across the fan. And so you get a 3D picture of the seafloor, so a 3D depth, 3D surface of the seafloor. That's one of the primary data sets that we use in the atlas and some of the data that we're showing, but we also use sound in a different way, where we penetrate down through the sediments at the seafloor and look at the layers of sediments at either very high resolution close to the seafloor or deeper down with using seismic reflection profiles. And then we can also do things like take ROVs down to the seafloor and take bottom photographs, or do slightly different sets of imagery with things called side scan imagery as well. And I'm going to show you some examples of all of those. I like to think of this as sort of remote sensing of the seafloor, in the same way that the satellites are moving around the globe and taking, sending down a pulse and then receiving the signal back and putting together these global pictures for the whole planet. And this is what we're doing on the ships, but working from a ship and sending a pulse down to the seafloor and getting that return signal. And we're using that all together to see what the story is on the seafloor. So I think the best way to talk about what's in the atlas is to just show you some of the most amazing imagery that we have. So I've just selected a few different images from around the globe of different things to show you what kind of things we've seen, and also why it's important, why they're interesting. So these are some really cool patterned ground or permafrost patterns from the Laptev Sea offshore eastern Siberia. This was in really shallow water. The water depths here are about 10 to 17 meters. And what's fascinating about these things is that, it shows you patterned ground that's very similar to what we see around the Arctic, the Arctic margins on terrestrial landscapes, on land today. But we found them in water, in the ocean, now submerged. And they're perfectly well preserved. That's one of the best things about looking at the seafloor rather than looking at terrestrial landscapes, is that often these features are very well preserved because there's no humans, there's no roads, there's no weathering to affect these features. And what these permafrost patterns tell us is that although this area was permanently frozen during the last glacial, it wasn't covered by grounded ice. So it was ice-free, but it was permanently frozen, and then there was thermal contraction, and it forms these polygonal patterns. And then about 6,000 or 8,000 years ago, when the sea levels rose again, these features were buried. So, this tells us exactly what the sort of environmental history of that area was, just from, some images from the seafloor. So here's one of my favourite images of iceberg plough marks. And this is where great big icebergs, which are carved from the ends of floating glaciers today, the bottom of them, or their keel, touches down on the seafloor and then drags through the sediment. And you can see that these are some of the most weird and wonderful, this is what I've called them, the weird and wonderful pictures of plough marks. And you can see the sort of fascinating patterns that they make. So if you look at the sort of orangey one with a loop, you see an iceberg sort of touched down, done a loop-the-loop, and then been whisked off or melted off, in another direction. The one with the, in the sort of top right, I think, as you're looking at it, an iceberg's come in, hit the sea floor, and then it looks like it's spun in a circle. And these icebergs, their motion is driven by currents and winds and also tides, but it looks like there's probably 2 or 3 different bits of the iceberg that was, as it was spinning round, has carved out that pattern. The one in the bottom left is a very wide iceberg plough mark, so it's several hundred meters wide. They're really low in relief, like very shallow, so only a few meters deep, but very wide features. And that's interesting because that tells us that these icebergs were probably carved from a floating ice shelf, so a tabular system, so much bigger ice shelves than we have in the Arctic today. So that was probably formed during the last deglaciation, sort of after 20,000 years ago, when big bits of ice were being broken off some of the big ice shelves up there. This is probably a sort of what I'd call a classic glacial terrain from the Amundsen Sea in West Antarctica. So this is in front of the Getz ice shelf. And here you can see a field of streamlined landforms. Some of them are just linear forms. Some of them have a sort of fatter head at the front, called a crag, and then a streamlined tail at the end. And you can really see the flow of ice in the past from right to left on your page. Sorry, I'm horrible with rights and lefts. From right to left on the page, and you can see how it's curved around the topography of the sea floor, and you can see exactly where ice was moving before. So, it's really great to have these imagery, and we've got it now at all this very high resolution, much higher resolution than we had about 20 years ago, which was when the last time an atlas of this nature was sort of tried to be put together. But what you can see from all of these things is that you get information about how ice sheets behaved in the past, how they flowed, how they stepped back, how they retreated, and that's really relevant to what's going on with our ice sheets today. If we can find information from the sea floor about what stabilizes ice when it retreats, or about how quickly it flows over different materials on the seafloor or at the bed, then it means that we can contribute that knowledge to the ice sheet modelers that are working in these areas today and say, actually, we know that X amount of the bed is covered by this very soft sediment, which we can actually go down and sample and grab, and we can give those physical properties to other workers in the area. This is my final image. That's a beautiful set of retreat moraines going back towards Canada, which is in the top left-hand part of your or part of the image. So the terrestrial Canada is in the top left-hand corner there. But yeah, I just hope that I've shown you, the importance of putting all of these images together in one place and being able to compare and contrast them globally, and also the kind of information that we can learn about past ice sheet behaviour and how we then are using that in our studies of the cryosphere and climatic change today. And I'd invite you all to come to, there'll be a talk on the Atlas tomorrow afternoon in our session at 3:30. So I'd invite you very much to come to that if you're interested. Thank you.
Thank you very much for your presentations. We'll now open the floor for questions. Would anyone have any questions here in the room?
Bob Berwin, freelance journalist. Jenny, do you have any speculations or thoughts on what might cause an increase in foehn winds in the future? Any sort of circulation processes that are occurring?
Yeah, their frequency is very closely related to the large-scale circulation in the area called the southern annular mode. And that's quite linked to the ozone hole, among other things. And over the last couple of decades, since around the 1960s, we've been in what's known as a positive phase of the southern annular mode. And that means that the winds have strengthened and also contracted towards the continents. So it's meaning that the winds are now crossing the peninsula more directly and also further south. So it's possible if SAM continues in a positive phase that either the winds will continue to strengthen or they will remain sort of as strong as they are now. And so that's something we need to look into as to whether they are able to increase the frequency of foehn into the future.
Jonathan Amos, BBC. Julian, I would like to have spoken to you about your paper when it came out, but I'll ask you the question that I had at the time, because I was doing something else. Really, why is the relationship that you plotted linear? I mean, I've got two brain cells, and the intuitive one in me says, where's the feedback? Where's the positive feedback? Where's the amplification that we've been talking about? So why does that not impact on that linear trend?
So, well, first off, one of the things that we're doing, we're doing a 30-year running mean trend for that. So we're definitely taking out that year-to-year variability that you get. So this is more sort of getting at that forcing. And basically we're looking at the energy balance at the ice edge and making some assumptions such that at least at the ice edge, the albedo, for example, and the temperature of the ice is not going to be changing. And so to keep the energy balance closed, basically the sea ice edge is going to have to migrate northwards in order to account for increase in the downwelling long wave. that is coming in because of increases in CO2. And the other assumptions that we made, at least in this paper, and it seems to hold at the timescales we were looking at, is that there's not any really large changes in ocean circulation or atmospheric circulation that would be advecting more heat in the Arctic on the timescales that we were looking at. Certainly on longer timescales, ocean circulation is very important as well. But basically, it was just sort of a simple energy balance model, keeping the model, the energy balance has to stay in equilibrium at the ice edge, which means the ice edge had to migrate further north.
Okay, and the other kind of question which James might want to pile into as well, I mean, we were surprised in 2005, we were surprised even more in 2007, and we were really surprised in 2012. So what I'm kind of wondering is have we regained our composure now? Do we think we understand the system better so that if something else happens, it's not going to be a big shock? We kind of think we've got a feel now for the way that the models a few years were just incapable of getting anywhere near.
Well, I think, these sort of dramatic events, so when you have large amounts of ice loss, I mean, those are definitely primarily driven by a combination of thinning ice, which, makes the ice pack more vulnerable, and then atmospheric circulation patterns that are really favorable for sea ice loss. So 2007 was a really good example, where you had just a perfect situation set up where you had a lot of warm air advection into the Arctic. You had a lot of motion pushing the ice towards the pole and advecting it out of the Fram Strait. And so it was sort of this perfect storm conditions to take away a lot of ice. But, those sorts of atmospheric circulation patterns have been in there in the past, but they didn't have quite the impact. And one of the things in my talk that I'm going to be showing later today is that I've noticed there's an increase in tendency for really rapid ice loss events in summer, which I define as losing 1 million square kilometers of sea ice within a week-long time period. And the probability of that happening has gone up dramatically in the last few decades. So, or actually just the last decade, really. So weather patterns that are more effective for removing ice are actually doing a really good job now, but we can't predict that. And so I think that's what's always much more difficult. I mean, you can't necessarily predict what the summer weather is going to do. So that makes it really hard for us to say, are we going to have a new record low this year? I mean, I think we're on thin ice, so I think the tendency, the possibility is there to break a new record low. But again, it's still going to depend on the weather. And earlier work that Marika Holland did, and I was on a study as well, is we were just looking at, at what point do you get to the point where the ice is thin enough where the atmospheric circulation pattern in summer no longer matters? I don't think we're quite there yet, but we're getting there where it probably won't matter so much anymore.
I just add, so 2012, on one hand, it was just a surprise because it was such a big drop. But then on the other hand, it's not a surprise because we have in the background this long-term decline. So we're expecting, each year there's a decline, the chance of a record low is going up. But the thing is, I guess there'll always be surprises in the sense that we can't predict the weather over the summer. So we can say that there's going to be increasing likelihood of record lows because we have this clear underlying trend, but there's always going to be some component of natural variability that is unpredictable. Mm-hmm. And regarding the models, there are clearly some models that do a very bad job and there are some models that do a better job, but as a whole, the models do okay in simulating the Arctic trend. They get it, they all go down, and they get it to within a reasonable magnitude. And we have to remember that we're comparing one realization of the real world, which we have, and then a model average, which only, when you take a model average, you're just looking at the forced component, so the man-made component. But in the real world, we have a mixture of man-made and natural. So you've got to be careful that you're not comparing like with like. And recent estimates suggest that 30 to 50%, so maybe up to a half of the observed trend, is naturally forced. So therefore, we would only expect the models to capture half of the observed trend. So we have to be careful when doing that comparison. So I think we have a pretty good understanding of what's going on in terms of the trend, but there will always be some unpredictable component on top of that.
Hi, Andy Coghlan, New Scientist. Couple of questions. First to Jenny. The Föhn winds. How do you pronounce it?
Föhn.
Föhn. Where do they come from, and why are they warm? And secondly, is this the first evidence that the glaciers and ice shelves are being melted from above as well as from below. We know that the seawater is sort of digging in underneath and doing it from below. But is this first time or first evidence that they're being sort of worn down from the top as well? But before you answer that, a quick one to James. Sorry, yeah. The 2045, 2046 predictions, is that with a 2-degree rise? I wasn't quite sure.
So we can either talk about this in terms of a temperature rise or a year, assuming some future pathway. So that the best estimate for a temperature rise we said was about 2.1 degrees, but it could be as early as 1.7. In terms of timing, so that's the 2040 kind of number, but it's somewhere between 2030 and 2050, say, depending on what our future emissions are.
But in that range, 1.7 to 2.1.
Yeah, it's kind of...
Yeah.
That seems to be the sensitivity in our results. That was the kind of temperature range where the probability of seeing an ice-free Arctic really ramped up. So you start getting a quite possible but quite low probability at 1.7. But by the time you get up to 2.1, then it's becoming quite more likely.
And I would just add, so the 1,000 gigaton target, that's basically the 2-degree temperature rise. And I think the only thing that I would say it's a bit different with what James and I did is that because we're looking at it from the observations, and the observations show a steeper dependency on cumulative CO2 than the models, I think that's why when we look at 1,000 gigatons of carbon, which is that 2-degree target, we don't have any sea ice left, whereas you still have a probability where there might be some at that target.
Yeah, but is it gone completely every year?
Yeah.
Okay.
Yeah.
But
again, natural variability could bring it back.
Well,
a little bit, yeah.
Yeah.
But
Yeah. Okay.
Mm-hmm.
Yeah.
Okay.
So Jenny.
Previously we had seen firn winds in individual case studies. A few week long case studies where we'd done really intensive observations and modelling studies. But this is kind of the first study to see how frequent they are, how spatially extensive they are, because from case studies you can't really find that sort of information out. So we can now sort of see that firn winds aren't only in summer, they're all year round, and that they can have a melting potential over a much wider area than we knew before. But in terms of how they happen in a number of places across the globe, really, wherever you get airflow that is perpendicular to the mountain. So the word firn is a German word because they were originally sort of identified over the Alps, and they're very prevalent in places like Innsbruck in Austria. They also happen over the Rockies in America, where they're called Chinook winds. They have a lot of regional names, but they are quite frequent over a number of places. But in terms of the Antarctic Peninsula, they happen because the Antarctic Peninsula is roughly north-south aligned, and the wind direction is roughly westerly. And the heating mechanisms I kind of touched on. So the one that we kind of see as the classical mechanism is where when the air approaches a mountain and it's forced to rise, it rises, and as it does, it cools at a rate of around 10 degrees per kilometre. So for every kilometre it rises, it cools at 10 degrees. Once cloud formation happens and precipitation, the air mass can then continue to rise, but at a slower rate of around 5 degrees per kilometres. So then once the air has gone past the mountain on its descent down the other side, it's kind of free to fall and heat up at the warmer rate of 10 degrees per kilometre. So you get an offset, so usually 5 to 10 degrees warmer at the equivalent altitude on the other side of the mountain. So that's what we kind of have thought about for a very long time, sort of since the late 1800s. There's also a few other mechanisms, sort of one's called isentropic drawdown, so that's where you can have, again, air passes over the mountain but at higher altitudes and kind of brings down through turbulent mixing the air that is warmer from above towards the surface. So those are the two kind of main mechanisms.
Is this first evidence that the ice shelves are being melted from above as well as from below?
I don't think it's necessarily the first evidence. I think there's quite a few papers out there before that have looked at firn case studies. but I think this is probably one of the largest spatial studies that we've looked at foehn winds over.
We have time for one more question.
Hello, just for Gillian, my name is Marie Leroux. I'm with Agence France Presse. I wanted to follow up on something you talked about the increase in sea ice variability, and firstly, I wanted to ask if you could help translate for me 2 standard deviations beyond the long-term mean for a layperson like myself. How would you? There must be a different way of saying that. And I wanted to just also ask if you could elaborate a bit on what you said, that this may be a sign that we're starting to transition to an ice-free period. Are you the first people to issue this warning? Is it? Should we be really afraid?
Oh, well, as a scientist, I always tend to be a bit more cautious. I mean, because there's a lot of natural variability in the climate system, but, certainly this instability where we see this increase in variability, I mean, it's definitely something we do see in climate models as you start to transition towards ice-free conditions. And I think what it really represents is that the ice covers become very, very thin. And so it's just that more vulnerable to anomalous forcings by the atmosphere. So that's why we're getting these larger swings. And in terms of the standard deviations, I mean, I guess another way to word it was every month of the year last year had more than 1 million square kilometers below the long-term mean. So that could be another way. But that's about just 2 standard deviations. But some were more like 1.5 to 2 million square kilometers below the long-term mean. So these are huge departures, and they're larger departures than you normally see in a climate data record. At least specifically going for the whole year. I mean, you had 7 months in 2016 that were at least 1 million square kilometers below the long-term mean, which is something we haven't really seen before in the data record.
Thank you very much. I'm afraid we have to finish here because we have another press conference coming up. But if you'd like to interview any of the scientists here, you can do so. You can book interview rooms at the press desk. And if any of you would like images from the atlas that Kelly showed, you can get in touch with Atina, who is the British Antarctic Survey press officer, and she'll give them to you. Thank you all very much for coming. Thank you very much for the interesting talks. And I hope to see you here at 10 for a press conference on plastic litter. Bye.
11.
Oh, yes, sorry. At 11.
1 in 20.
Thanks. Good morning, everyone. Welcome to our second press conference today, and we'll focus on the polar regions. The title is Polar Regions, Arctic Sea Ice Future, Antarctic Ice Shelf Stability, and Glacial Landforms. Taking part in this press conference, we have Julian Strove, who is a senior research scientist at the University of Colorado National Snow and Ice Data Center in the US. Following her talk, we'll have James Screen, who is a senior lecturer at the Department of Mathematics at the University of Exeter in the UK. And they will focus on the Arctic. And then we'll have 2 speakers from the British Antarctic Survey, Jenny Thornton, who is a PhD student at BAS and also at the University of Leeds in the UK, and Kelly Hogan, who is a marine geophysicist at BAS in the UK. And I'll hand over to our speakers, and at the end, we'll open the floor for questions. Thank you.
Okay, great, thanks. I should probably first mention that I'm also at University College London now, so I sort of had a joint affiliation between both institutes. That's something we hadn't seen before. I mean, we had several consecutive months with record low sea ice conditions. And of course, because of that, we had the lowest annual extent that we've recorded yet in the Arctic in 2016. And if we just look at where we are today, when we add on the last 3 months in January, February, March, again, we're tracking at the lowest levels that we've seen. So we're looking at, almost 7 consecutive months now where we've had record low sea ice conditions. And this isn't something that we've seen before, definitely in the satellite data record. And, it's a little bit cautious when we think about this because just because we have these record low winter ice conditions, that doesn't necessarily mean we're going to have a record low summer sea ice extent. There really is little correlation between what happens in winter in terms of the extent and what's going to happen in summer. So there's a bit of a danger there in trying to extrapolate too far in the future. But what does matter is how thin or thick that ice is. And I actually just came back from the Arctic on Friday. I was up there for 3 weeks out in the sea ice extent. You can see that the trends are about half of what we see for the Arctic, about 43,000 square kilometers per year versus 87,000 square kilometers per year for September. But what's interesting is the last 3 winters have had the lowest record maximum. And I don't think we've really seen that before, where we have 3 consecutive winters in a row with record low sea ice conditions in the wintertime in the Arctic. And the region that's really driving this is the Barents Sea ice. So in the Barents Sea, we seem to have persistently low sea ice cover that keeps continuing several winters in a row. And that's really what drives our winter sea ice variability. So whatever happens in the Barents Sea basically sets the stage for the Arctic as a whole during wintertime. Now, 2016 was quite unusual in many ways. And in one way, I mean, every month of the year in 2016 saw a sea ice extent that was at least 2 standard deviations below the long-term mean. And some months, May and June and October and November, were more than 3 standard deviations below the long-term mean. And so I just want to make that clear. So I'm going to talk about the shrinking sea ice, which I know everybody is probably well aware of this topic. But just to set the stage, we're just showing the time series from the satellite data record, which shows the September sea ice extent from 1979 to 2016. And the one thing I think that's interesting about what's going on in the Arctic right now is, I mean, there's a lot of year-to-year variability, but certainly we have this long-term trend, which is about 14% per decade right now in regards to the summer sea ice extent. But there is a lot of year-to-year variability, but the last 10 years have all seen the 10 lowest sea ice extents on record. And 2016 didn't set a new record low, but what I'm going to talk about in a moment is just how anomalous 2016 was in many other ways besides setting a new record low. And in wintertime, so we usually focus on the summertime because that's when the changes are most dramatic right now in the Arctic, but the winter is starting to respond as well. If you look at the time series of just the winter Lincoln Sea, and we were making snow depths and sea ice thickness measurements, and we found that in general the first year ice was a bit thinner than usual, and it's not surprising because we had a very warm winter in the Arctic, so that would have impacted somewhat on the thermodynamic ice growth. We did find the multi-year ice was about 2.5 meters thick, so again a bit thinner than we may expect. So that's something I think to look at more is how thick the ice is going to be as we come into the melt season. And excuse me, just to talk about kind of where we are today, I mean, we're still tracking at record low levels so far. This was just from a couple days ago, but currently sea ice extent again is still tracking at record low levels. And so it's going to be really interesting to see how this continues. In the summer, we did see, right when I was leaving the Arctic, some strong winds were starting to generate open water areas. So things are starting to break up now in the Arctic. So I think it's going to be an exciting summer. One of the things that I will